In this module, we'll be looking at the definition of moment of inertia so that when we look at structural members like beams and columns, we'll be able to understand why they have cross-sectional shapes like an H or an I or a C. Why don't they have a solid rectangular, square, or circular cross-sectional area? That's a question you'll be able to answer after this module. And we'll look at what primary property of these members influences the design decision. So it's very important to understand why we use I-beams. You'll understand that after this module. Some of the applications to consider are we find that many structural members are made of tubes rather than solid squares or rounds. Why might that be? It turns out that the answer to this is that the tube will have a lot of its area pushed out, a lot of the mass in the area out at the outer edges or the outer limits of the column. And it turns out that thrusting of the material away from the centroid is key to making them having the property that we're looking for to reduce bending. This section of the book covers some parameters of the cross-sectional area that influences the designer's selection of what type of beam or column to use. Do you know how to determine the value of these parameters for a given cross-sectional area? Probably not yet, but you will soon. Looking first at the definition of moment of inertia for areas, consider a plate submerged in a liquid. The pressure of a liquid at a distance y below the surface is given by the pressure is equal to gamma, the unit weight of the fluid, liquid that you're using, and y, the distance below the top of the fluid. So gamma is the specific weight of the liquid. The force on the area dA at the point dF is given by the pressure acting across that differential area dA. The moment about the x-axis due to this force is y is times dF, and the total moment is found by integrating across the entire cross-sectional area y times dF. And that might be expanded as shown here to give the integration that you see, but that will depend on the shape of the plate submerged into the liquid and its dimension and also the specific gravity of the fluid. This sort of integral term also appears in solid mechanics when determining stresses and deflections. The integral term is referred to as the moment of inertia of the area of the plate about an axis, and it in this application it would influence if you wanted to design an effective paddle for a canoe. It would show you how the shape of that paddle would influence its efficacy in providing, forward momentum for a canoe. But we'll more typically be looking at these applications in terms of designing a beam to have the type of deflection properties that we need. To define the definition of moments of inertia for different areas depends on their shape, and you can please consider the three different possible cross-sectional shapes shown here on the left, A, B, C. And if we were going to make a beam out of each of these different areas and apply it with a pin on the left at R and a roller at S and apply a load P on the beam, if all the beams have the same total area, and assuming they are made of the same material, they'll have the same mass per unit length. So would the deflection be the same for all three beams? For the given vertical loading P on the beam shown on the right, which shape would develop less internal stress and deflection, and why? Well, the answer is the one on the left will have the least amount of deflection, and the reason why is because a lot of its area is moved away from the centroid. You see the line right through the center of the beam. You see an awful lot of the area in that beam is relatively far from that line of center axis of the beam, and that's the property that we're going to be able to now calculate, this property of moment of inertia that will help us understand why the beam A is going to be the one that has the least deflection. So the answer depends on the moment of inertia of the beam. It turns out section A has the highest moment of inertia because most of the area is further away from the x-axis. Hence, it has the least stress and deflection. For differential areas shown in the figure, if we calculate a differential inertia about the x-axis, we'd get y squared times dA. If we want to calculate the moment of inertia about the y-axis, we would take x squared times dA. And if we wanted to calculate the polar moment of inertia, which we sometimes do with a column, we would calculate the differential J0, which would be the radius of a differential ring times dA. The moments of inertia for an entire area are obtained by integration of this task. So if you want to calculate the moment of inertia about the x-axis, we have to integrate across the entire area y squared dA. For the moment of inertia about y, we would integrate across the entire area x squared dA. And if you wanted to calculate the polar moment of inertia, you would have to integrate on r. But you can also get the polar moment of inertia as a combination of the moment of inertia about x and about y. So you'll see that at the right, where J0 is equal to Ix plus Iy. The moment of inertia is also referred to as the second moment of an area and has the units of length to the fourth power. So you might have meters squared or inches squared or millimeters to, not squared, meters to the fourth or inches to the fourth or even millimeters to the fourth, depending on the size of the area that we're looking at. If you want to complete this integration, and we'll be doing very few of these, but if you wanted to complete this task using integration, we would, for simplicity, the area element used as a differential size in only one direction, either dx or dy. This results in a single integration and is usually simpler than doing double integration with two differentials. Our step-by-step procedure is first to choose an element dA, and there are two choices basically, either a vertical strip or horizontal strip. And some influences in your choices are the element parallel to the area about which the moment of inertia is to be determined usually results in an easier solution. For example, we typically use a horizontal strip for determining Ix and a vertical strip for determining Iy. If y is easily expressed in terms of x, then choosing a vertical strip with differential element dx wide may be advantageous. Then we integrate to find the moment of inertia. For example, given the element shown in the figure above, we would calculate Iy equal to the integral across the area x squared dA. And for our expression in this example, we would then have x squared times whatever the function in terms of y is, or whatever y is in terms of x, times dx. And similarly, for Ix, we would say we can find the integral as the differential integration of inertia across x being equal to 1/3 y cubed dx. And that's using the parallel axis theorem that's described in example 10.2 of the textbook. Since the differential element is dx, y needs to be expressed in terms of x, so it needs to be some function of x, and the integral limits must also be in terms of x. And as you can see, choosing the element and the integrating can be challenging it, It may require a trial and error approach, plus you'll gain competence through experience. Example where we have y cubed equals x squared, and we want to take this shape and find the moment of inertia about the x and y axes. We'll follow the outlined steps in the previous slides. For our solution, we'll just say Ix is equal to the integral across the area of y squared dA. And in this case, the differential area is 1 minus x, because the right side for any slice is at 1 meters, and the left edge is whatever x is at that point. So we could say that the differential area is also equal to 1 minus, and here we know the x is equal to y to the 3 halves. So now our differential area has that particular term, quantity 1 minus y to the 3 halves times dy. Now when we substitute that into our first equation, we get the moment of inertia about x being equal to the integral from 0 to 1. We're integrating on y, so y goes from 0 to 1, and we're integrating y squared times dA, which is y squared times the quantity 1 minus y to the 3 halves times dy. And if you complete this integration task, no easy feat, I assure you, but you can be done. It's not that hard a task to integrate a polynomial like this. We can get that the moment of inertia is equal to 0.111 meters to the fourth. Continuing with this example, we still want to find Iy. In this case, we'll use a vertical slice, and here we have the integral across the area of x squared dA, and this is relatively easy because we know what we're going to have an easier relationship between the two variables in this case. The moment of inertia about y is equal to, on the upper right, the integral of x squared times y dx, and then we can substitute the fact that we know that the function y cubed equals x squared could also be said as y is equal to x to the 2/3. So our integral becomes the integral of x squared times x to the 2/3 times dx. This one's an easier one to integrate, and we can integrate from 0 to 1 to find that the moment of inertia in this case is equal to 0.273 meters to the fourth. So we found the moment of inertia for about either axis. It's also possible that you could use a vertical strip to calculate Ix in this case, but you get the same answer that we got in the previous example. If we look at composite areas, and we will, that will be an area that we're going to emphasize, is it's going to be possible to consider each of the individual shapes that comprise the composite member in order to calculate the composite moment of inertia. We often make beams and columns out of this type of combining of different areas to save money and to build structures that are relatively lightweight but sufficiently strong to meet our needs. If it is helpful and efficient for you to, you can do a simpler method for determining the moment of inertia of these types of cross-sectional areas as compared to the integration method. So we probably won't need, we won't need to integrate when we're doing composite areas in this course, but in actual applications you might, but we're going to keep our shapes relatively straightforward. Any ideas on how this problem might be approached? In the same way that we were looking at composite areas in centroids in the previous chapter, we're going to be able to use a similar approach here. Look at some applications. This is another example of a structural member with a composite cross-sectional area. Such assemblies are often referred to as a built-up beam or member made up of other components. These are made of wood strips that are fixed together. Design calculations typically require use of moment of inertia for these cross-sectional areas. In fact, we pick their shapes based on their moment of inertia very commonly. A composite area is made up of made by adding or subtracting a series of simple shapes like rectangles, triangles, and circles. For example, in the area on the left, it can be seen as a rectangle plus a triangle minus an interior rectangle. So we have three composite areas making up the single piece shown on the left. The moment of inertia about their centroidal axes of these simpler shapes are found in most engineering handbooks and with a sampling on the back cover of the textbook. When using data and the parallel axis theorem, the moment of inertia for composite areas can be easily calculated. The steps for analysis of a composite area is to divide the area into simpler shapes. So we take a rectangle with a hole in it and let it be a whole rectangle minus the a body that has the shape of the hole, but which will now have a negative mass. So we'll be adding those together or subtracting the whole, the circular area out of the rectangle. So we then next locate the centroid of each part and indicate its perpendicular distance from the centroid to the desired reference axis. Then we determine the moment of inertia of each of the simpler shaped parts about the desired reference axis using what's called the parallel axis theorem. So we can find the moment of inertia about the x-axis by finding the moment of inertia about the x prime axis plus the area times the distance between those two axes squared. That's the parallel axis theorem that we'll be using in these composite areas. The moment of inertia of the entire area about the reference axis is determined by performing the algebraic summation of the individual moment of inertias obtained from steps 3. Please note that the moment of inertia of the whole is subtracted, therefore. Consider this example where we've got beam's cross-sectional area is shown. So we've got three different rectangular areas, and we want to calculate the moment of inertia about the area of the entire area about the x-axis. So we follow these simple steps. First, we calculate the cross-sectional. We can see that the cross-sectional area can be divided into three rectangles, 1, 2, and 3. Next, the centroids of each of the three rectangles are in their center, and we know how to calculate that. We can then get the distance from those centers to the x-axis as a simple geometric task, and in this case it's 175 millimeters, 0 millimeters, and minus 175 millimeters respectively. Now it's time. Continuing the example, we'll need the equation for the moment of inertia of a rectangle about its centroidal axis, and you'll find that in the textbook as 1/12 b times h cubed, where you have to remember what b and h cubed are. B is its thickness and h is its height cubed. So we'll start with the central rectangle, which is easier because the centroid of the center rectangle happens to go through the centroid or the x-axis of the entire beam. So it's just equal to 1/12 its thickness, 50 millimeters, times its height, 300 millimeters cubed, or 1.125 times 10 to the 8th millimeters to the 4th. Next, consider the upper plate, which happens to be equal to the lower plate. And for either of these, and first focus on the upper plate, we can think of it as calculating. First part of the first term is the moment of inertia about its own axis plus the area of that component times the distance between the axes of the upper rectangle and the x-axis. So in our first, in this, considering the upper plate, we have 1/12 its width, 200 millimeters, times its height, 50 millimeters cubed. But then we have to recognize that it's lifted far above or below the x-axis, so we need its area, 200 millimeters times 50 millimeters, times the distance from the centroid of the upper plate to the x-axis, 175 millimeters squared. So the contribution from the upper plate and the lower plate is equal to 3.083 times 10 to the 8th millimeters to the fourth. Continuing this example, we now just need to sum the three answers that we got, the contribution from the upper plate, the middle plate, and the lower plate together to get the composite moment of inertia, 7.291 times 10 to the 8th millimeters to the fourth. In another example, take a look at the blue shaded area in the figure. If we want to calculate the moment of inertia of the area about its x-axis, then we need to find out how to make up the blue area through a combination of simple shapes. And there's more than one way to do this, but one way that we can do it is to recognize that if we take the entire rectangle from the rectangle A, that is a total of 350 millimeters wide and 300 millimeters high, so the entire larger rectangle, and if we have a whole rectangle minus a triangular slice labeled C and the whole circular hole at B, we'll be able to find those three areas make up the whole composite cross section. And you can find the information about centroids of the simpler shapes on the inside back cover of the textbook, and we can get the perpendicular distance of the centroids of each of these shapes from the x-axis. So we can do that and find that the distance for the entire rectangle is 150 millimeters, so the centroid goes through the line, the axis of symmetry halfway up down to the x-axis. Then we want the distance B to the circular hole, and that's also 150 millimeters. And we can get, since the longer leg of the triangle C is 300 millimeters, we know that its centroid is 200 millimeters up, so that's how we get that distance C is equal to 200 millimeters. If we calculate the moment of inertia contribution from each of these areas, we get the equation shown, where we're just looking at the individual calculations that come from the inside cover of the book. And if I want you to, I'll want you to be able to know how to use those tables, but I don't want you to have to memorize any of those tabled formulas. And we can calculate that moment of inertia for each of these. But remember that the only whole one was the larger rectangle A. And then we had two holes represented by B and C, so that when we want the moment of inertia, we have to remember that we have one positive and two negative components. So we have IXA minus IXB minus IXC to get a total of 1.715 times 10 to the 9th millimeters to the fourth.